Hello, this is Professor Keen. This is another lecture on Newton's Principia. I'm looking at Book 1, Section 2, and in my last lecture we talked about his Proposition 1 or Theorem 1. And recall that in that proposition he was talking about what happens when there's an object, you might think of like an asteroid hurtling through space, for example, an object that's traveling in a straight line. According to Newton's first law, it's going to continue in a straight line. But then if it feels a force directed toward a point, its trajectory is deflected. And what Proposition 1, Theorem 1 talks about is what are the implications of a centripetal force that is acting on an object. And the important things that he came up with in this proposition was that as this object is feeling a centripetal force, it remains in the same plane of orbit. That's point number one. And point number two, if you consider some time interval while it's in orbit, the area that is swept out by a line connecting the body to the center of force, that radius sweeps out an area that is proportional to the time of the orbit. So that were the main two conclusions that we arrived at in his Proposition 1 or Theorem 1. The next thing that Newton talks about are some of the corollaries that follow from this proposition, or that are related to this proposition. I don't want to spend any time going through the four corollaries that come right after it. I want to jump right into his Proposition 2, Theorem 2. So let me mention what this is. This is Proposition 2 or Theorem 2. And what you can think about this theorem is the converse of Proposition 1, Theorem 1. This is the converse of Proposition 1 or Theorem 1. Okay, so let me just write out what his Proposition 2, Theorem 2 is, and then I'll explain this briefly. It's actually a pretty easy one to understand. So he mentions that every body that moves in a curved line, first of all, that is described in a plane, or described, he says, in a plane. That means this curved line lies in a plane. So you might think about the plane of this page that I'm writing on, and so there's some curved line that lies in the plane. And secondly, if this body that's moving in a curved line not only lies in a plane, but is by radius drawn to a point, either immovable or moving forward with a uniform rectilinear motion. I'll explain what that means in a moment. Rectilinear, let me go back. Rectilinear motion describes by radius drawn to a point, either immovable or moving forward with a uniform rectilinear motion, describes about that point areas proportional to the times. This body is urged by a centripetal force. Directed to that point. So what is he saying here? He's saying if you see some body, some object that's moving along a curve, and that curve lies in a plane, like the plane of this board, and if you draw, if it's moving about some point, And if you draw a radius to that object and you look at the area that is swept out by that radius as it moves along, okay, so if we take equal increments of time and you're watching this radius sweep out these areas, so this area during the first unit of time, and this area during the next unit of time, and this area during the next unit of time, if all those are equal to each other, then we know that that object is experiencing a centripetal force toward this point. So notice what he's doing here. He's saying that in his proposition 1, theorem 1, he said, what happens if there's a centripetal force acting on a body? Well, then we know that it is going to stay in a plane and sweep out equal areas in equal times. In this proposition, he's saying, well, what if you see some object that's moving in a curve that lies in a plane, and we see that it's sweeping out equal areas in equal times, or area proportional to time? Well, then we know that it must be feeling a centripetal force. So, whereas proposition 1, theorem 1, said if there's a centripetal force, then there's going to be a certain, the motion behaves in a certain way. So if that, then that. Whereas proposition 2, theorem 2, says if the motion behaves in a certain way, then you can infer that there must be a centripetal force. So really, these two are converses of one another. And there's one other point that he makes in here, that this radius line is drawn to a point, and this point here is either immovable, that it's sitting still, or he says it could be moving forward with a uniform straight line motion. So for example, if this whole thing was moving with this direction, you can still say that there's a centripetal force going toward this point. Okay, this proposition 2, theorem 2, is going to be very important, because he's going to say, well, why shouldn't we just take this kind of motion in a plane, sweeping out equal areas in equal time, why don't we just use that as an indicator of a centripetal force? And so he's going to later on say, well, if you're looking at the motion, for instance, of Saturn, and it's going around the sun, and it's sweeping out equal areas in equal times, and it's lying in a certain orbital plane, then we can conclude that there must be a force that's aimed at the sun. So he's going to use this to develop his universal law of gravity. Remember, the idea here is that people had a notion of gravity that was the ancient and traditional view of gravity is just sort of a heaviness that objects feel when they're near the Earth. There's not this notion of gravity, a force pulling the Earth to the sun or the moon toward the Earth. So what Newton's doing here is he's building up this mathematical apparatus in order to logically deduce the existence of a centripetal force pulling the planets toward the sun, and he's going to call that the gravitational force. Okay, before I jump into the next section, where he's going to develop some various propositions, I wanted to kind of give you a warning. There's going to be a little bit more mathematics in the next couple of lectures. So you're just going to need to sort of bear with me for the next couple of lectures, where I'm going through some of the mathematical aspects of Newton's Principia. Once we get over that hump, then it's going to be really easy to develop his law of gravity. So I'll pause there, and in the next lecture, I will begin talking about proposition 4.